Hello and welcome back. We're coming to you from the Mayor's Room in our downtown offices. Today's topic is correlation and regression. So let's begin. This is presentation 10.4. The materials in your workbook and textbook, chapter 10. We want to acknowledge the development team of Brad, Spencer, and Amanda. To illustrate our theory, we want to look at the degree to which one can predict success in first-year statistics course on the basis of one's high school math mark. And as you can see here, this is associated with predictability. And here we have the high school mark versus the college mark. Notice these are recorded as simultaneously or related, so they're dependent. Here's the graph of college stats marks versus high school. As you can see, there is an upward trend here, a mild trend, but look at the degree to which those data points fluctuate about the regression line. A very mild form. Here's the Excel output. We're going to focus on that here. And we're going to look at R square, 0.162. We're suggesting that 16.3% of the changes in college stats mark can be associated with or attributed to changes in the high school mark. We're going to assume a linear trend here, and that gives rise to this regression equation. And the intercept and slope are given here at the bottom in the Excel output. Substituting those in here, we have our regression equation. It's also called the least squares line, which we'll address later. The slope delta y over delta x, as you can see here, is the regular slope, but in this case, it's the changes in the college stats mark relative to changes in the high school math mark, and that value is 0.652. which suggests that when this denominator is 1, this numerator becomes the slope. And we're suggesting that represents the average change in college stats mark per unit change in high school mark. Now we'll look at prediction. We want to look at high school mark of 65. What's the best prediction of college level statistics? It's a matter of simple substitution, 63.6. Now we're going to do a test of slope of this regression line here, test of B1 here, and these statistics are all contained here in this bottom row. We'll address these as we go. The null hypothesization slope of the regression line, not significantly different from 0. The alternative, it is significantly different from 0. Now the test statistic follows a t-distribution with n-2 or 19 degrees of freedom. And we've checked that out. This represents the critical values of minus plus 2.093, and this becomes our test criteria. Now let's look at the evidence. Once we've got our test criteria in place, what's the evidence we have? Well, it's the observed value, B1, which in this case is coming on the screen here now, 0.652. Hypothetically, above is 0. And the standard error in the estimate 0.339, and that comes from down here, the Excel output. This gives rise to the t-statistic, or t-observed, of 1.922, again down here. And this is less than the critical value. So we would conclude that this is insufficient evidence to reject H0. The p-value, again, is down here, 0.07, 7% chance of observing a B1 of 0.652 or greater when the true slope is 0. So it's not unusual. Look at a confidence interval, which are observed 0.6515 plus or minus my t critical, which is the same as our critical value above, times the standard error, and there gives rise to our confidence interval for your beta. And as you can see here on the screen comes these two triangles with different slopes. When delta x equals 1, this change in height here of this triangle becomes the confidence interval for the slope. Now we're going to look at the variability involved. In the first illustration here, we have when we have no predictor variable and we just graph the college stats mark, more or less in random order or by a listing number. You can see here that there's no tendency for y to change according to this x values here, which are just random, and this represents the deviations about y bar. So where no predictor variables available, this prediction of college statistics marks is the average. Once we introduce x as a predictive variable, you can see here that that horizontal line in the left case here twists, and now we have this new line which reflects the influence here of the x values, which is your high school math mark. And over here on the far right, we're suggesting that these deviations of these red dots about the regression line are called random error or unknown variables that we have not addressed. Here we have the table of deviations, and you can see here, note the average y bar is down here, and we're going to look at these deviations here. There's 3 of them coming on the screen here. These are deviations of y from y bar, y prime from y bar, and deviations about the regression line. And we're going to start here. Look at x equals 64.4, and in this case we want y minus y bar. Y is 79.7, y bar 67.03. That difference squared is 160.3, and that represents one of these deviations here from y bar. Continuing, we need to find our y prime. When x is 64.4, we substitute in here and get our value 63.12. That represents a point exactly on this regression line. Now the deviations of y prime from y bar, that's the degree of this twisting of the regression line about or from the y bar. It is y prime, which is 63.12, minus y bar, and that value is 15.29, which suggests that it's one of these central points here. And finally, we're going to look at the error version. The error, in this case on the far right, is your y minus y prime. The distance from the data points y to the y prime. That difference squared, 274.90. Now we're going to look at these totals here. The total deviations, y from y bar, 4477.55. The deviations of the points, if they were on this regression line, from y bar, 730.15. And finally, the deviations of the data points about the regression line, 3748.48. And we're suggesting that when we're talking about regression, this becomes a sum. The sum of regression plus error sum of squares is equal to total. And that will occur when this is the least of all possible lines, hence the term least squared. Now look at the coefficient of determination. It is the ratio of this value, 730.15, over the total sum of squares. There we have it. As you can see, it's very small. It's saying that this twisting is small relative to the data points themselves. 16.3% of the square deviations of y from y bar can be associated with changes in x. The remaining 83.7% are associated with random errors or factors or variables which we've not included in our model. Well, that brings to an end presentation 10.7.4. We ask you to review it once again, take notes, and go to presentation 10.5.